that only 5–10% of the data has been actually used, usually in retrospective. And the reason is that humans cannot analyze or manage so much data in real time. If we want to move from forensics and post-crime analysis to crime prevention, if we want these systems to respond in real time, we must build smarter and autonomous systems. So we're talking about smart things with sensors, and obviously camera is the ultimate sensor with so much data generated. The system we're talking about is a system of systems. We're looking not only at one camera that can monitor the traffic, weather, and more. We're looking at the full system, maybe millions of cameras connected to hubs, connected to the clouds, connected to big data analysis systems, connected to each other's, to other systems. The big opportunities are coming from analyzing all these data and combining all these systems together. And we see such systems being built for many different industries. It could be surveillance, automotive, industrial robots, and many more. Each industry may have different devices with very different capabilities and limitations. For example, a camera mounted to a car may need to detect pedestrians at 30 frames per second at 100 watts, while surveillance camera might settle for 10 frames per second but will only have 1 watt to operate. So there are few reasons why all of these new capabilities that looked like science fictions a few years ago are possible today. Huge improvements in computation power and network bandwidth are the main reasons, but others are advances in deep learning algorithms and more. So we see a huge progress in deep learning that enable us to use predefined, pre-trained models in a more robust way than in the past, with higher accuracy across a broader range of objects. And we will see more capabilities improved, added, or combined to create more usages. For example, you can see a deep learning model used to detect a car, and then we can use another deep learning model to detect the color of the car, and then use the output of these inference to detect the model of the car, what's the license plate number, and maybe even recognize the person behind the wheel. Are you the owner of the car? A huge progress in deep learning will enable us not only to do deep learning, to use deep learning on a static frame, but across frames to detect scenarios. You can see here, for example, we detect people in a store. We can track them across frames, so we know their vector of movement, and then we can derive their intentions from their clothes, movement, and behavior, and try to alert the store owner that the ones marked red are potential thieves. Of course, we need to tune the algorithms or the deep learning models to its specific case and use specific data set for the best results, but the basic operation looks the same, and the underlying algorithms and capabilities looks essentially alike across all of these industries. So these operations of computer vision, deep learning, inference are very compute intensive. We usually need dedicated hardware acceleration in order to run them efficiently. Compute efficiency is a key, and it could be achieved in multiple levels, device level or system level. The first thing to do is to choose the best hardware for a specific task. The graph on the right tries to illustrate the trade-offs of using different silicon devices. For example, using a general purpose CPU on the right-hand side usually gives the best flexibility. There are many tools to compile, debug, and analyze such code There will be more developers available to code it. Such code will be portable to many available versions of CPUs. On the left-hand side, the other side of the scale, when you move to dedicated hardware, you get much better performance and efficiency, but many times the programming model is totally different. It's usually due to the nature of the task being accelerated. So you need different expertise, use a unique, less common API, less tools, less portability, and so on. This is a trade-off. So we would like to consider what the compute efficiency for each of these devices, how fast a task can be parallelized on this device, what the power consumption, what the memory footprint of this device is important because this device might not be able to run the deep learning models that has too big weights or will not be able to run inference with high batches. And of course, programming model is a major factor to code portability and time to market. Today, many of these systems are heterogeneous, so they will have a CPU and a GPU and maybe an accelerator like an FPGA card. What task to run on each device? How all these tasks been scheduled? How do they communicate with each other? Many questions, and we'll try to answer some of them. So it's obvious that we need a variety of devices, of systems. And the good news is that Intel has a wide variety of systems to choose from. Let's look at three different categories. The first one is smart cameras or edge devices. And people here will care about the physical constraints, the power and size. It's usually cost sensitive. Performance efficiency is important. Latency is important for real-time use cases. So a common performance indicator might be performance per watt. Looking at the next category, gateway, NVR, fog, I've seen many names to these, and it's pretty wide. These devices ingest and process multiple camera streams simultaneously, sometimes hundreds of them. They need strong media capabilities, decoding, encoding, and also we will see gradually multi-channel inference or multi-model models running here. Channel density is a key. Performance per dollar is an interesting criteria. The last category is a data center or cloud. It's usually less cost sensitive, seeking for high density media and deep learning throughput with flexibility to scale. So absolute performance throughput will be the key here. And three categories we can offer, a variety of devices. First, we can offer a wide range of CPUs and GPUs. You can start with an Atom-based CPU operating at 6 watt or less, moving to core CPUs that can operate at a very wide range of performance and power envelopes, all the way up to Xeon CPU monsters for the clouds. Most of these CPUs will have an integrated silicon graphic, what we call GPU. Some of these GPU are pretty powerful and can accelerate inference, decode, encode with high efficiency. We'll talk about it later. Intel also offer FPGA-based solutions by Altera with varying amount of logic and memory per segment from Cyclone 10 to the edge through ARIA 10 to NVR range and up to Stratix 10 for the cloud. We're also offering Movidius-based systems for edge cameras with very high deep learning efficiency at 1-2 watt. So designing the full network is our target. We're not talking about one device. This network will have many compute nodes, sometimes of different architecture, different operating system, different file formats, bit rates, etc. So we said that the first thing is to understand what's the most efficient device to run our task. Is it a CPU, GPU, FPGA? We'll see that in a minute. Second, where is the best place to run these tasks. People already understand that today, if they want to do better, they want to be more efficient, they have to push more compute to the edge. If the camera itself is capable of filtering out the non-interesting scenarios and can detect only the real ones, it can act faster without the need to go to the cloud and back. If this camera is already filtering most of the clutter, we can transfer upstream only the interesting scenarios, save a lot of bandwidth, a lot of storage, etc. So in order to be able to simulate and to demonstrate such a network, such a pipeline, we build a generic pipeline that is simple enough to be understood, but can also represent very complex systems. If you're designing an end-to-end systems, these are probably the pipeline stages or component you deal with. The code for this pipeline with the full explanations could be found as part of the Openvino tutorials. So look for it, build the tutorial, try to run it. Look at the pipeline stage by stage. So the first one is decode. Real systems usually use compressed video streams as the input, so video has to be first decoded before processed. In real systems, this stage can be representing decoding of 100 channels in parallel, each with a different resolution or format. The next stage is pre-processing, and this stage represents all the image processing computer vision required before the deep learning inference stage. For example, most deep learning models are processing smaller images, so this stage will have to choose a region of interest inside the original image or resize it. Sometimes image processing is required to match the format or the image quality or many other computer vision operations. Inference is a new main capabilities. We'll talk about it in a second. Post-processing is representing all the processing required after the inference stage is done. For example, in classification, you want to find the label and possibly render it to the right place in the image, or maybe not present it if the contrast level is not high enough. If we're doing detection, we would like to present a rectangular over the object we detected, and so on. And the last stage is the encode, which represent the final encoding of the resulting video before sending it up to the cloud for further analysis or for storage. The main software tools we'd like to focus on here are described. You can see the libraries with pre-optimized code, tools like debuggers, analyzers, and SDKs. We'll focus on Media SDK and Openvino, what used to be called Computer Vision SDK. And specifically, we would like to use the Openvino for the inference part and the image processing parts. And we'd like to use Media SDK to accelerate the decode, encode, and image processing, and use Intel System Studio. Specifically, I'd like to show you the use of VTune, which is part of Intel System Studio, for performance analysis of the full pipeline. So let's talk about inference. We want to first take a model that is already trained. Training deep learning model is not the scope of this presentation. Intel does have solution for that. Google it. It's easy to find. Openvino can process models that were trained by Caffe, TensorFlow, MXNet, and many software suites in the future. Then we want to prepare the model for inference. This model was trained usually in a cloud environment. Here it has to be used in different, more restrictive conditions. So we use the model optimizer to prepare it. Then we use the Inference Engine to actually do the inference. We want to be able to run the same model on different devices. So each device has its own plugin optimized for it. Then we might want to extend the model and create our own customized layer, which is also supported. So the first thing is to get a pre-trained model. You can get it from the internet. You can train it yourself. Or you could simply use our utility, which we call Model Downloader, that can bring the model to you. On top of many publicly available models, Intel also provides some state-of-the-art deep learning models for age and gender classification, face and person detection, car license plate recognition, vehicle attributes, many more. These models are part of the Openvino download package. They're free. Use them. So I'm downloading SqueezeNet 1.1 model from the internet. You can see that I type model downloader, the name of the model, and basically that's all. As you can see, two files were downloaded. We got the prototext file, which is basically the text representation of the topology, and we got the cafe model, which is a binary file holding the weights. So I got a model, and now let's prepare the model that we have downloaded and get it ready for inference. We will use the model optimizer to process the model. It's an easy-to-use Python-based workflow on a command line. It converts the model from the cafe, TensorFlow, or other to one intermediate format we call IR for intermediate representation. It's optimizing the topology by node merging, batch normalization, and other techniques. It can convert the format of the data from FP32 to FP16 or integer 8 in the future, and it can do all kind of manipulations to the network topology. You can add operations like scaling, normalization. You can remove subgraphs. So it's a pretty powerful tool. And running Model Optimizer is easy. Here I'm taking the SqueezeNet model that I've downloaded before and prepared it for inference. And I prepare it for inference and I'm converting it through FP16. So let's see it one by one. I'm running Model Optimizer.python. I am using the cafe model that I have downloaded, and I want to have it in FP16. That's all. And it's running. It's really fast. And you can see that two files are generated. An XML file describing the connectivity and a bin file that holds the weights. So I have a model ready for inference. So now let's use the Inference Engine to run inference using the model I prepared. So the Inference Engine is an inference solution. It provides seamless integration with application logic. The API is very simple, and the flow is very few stages. The first stage is all kind of definitions. We have to define the device to use. We have to set the batch size, etc. Then we load the model in an IR format, which is the output of the model optimizer from last stage. Then we define an input and output data structure, what's so-called blobs. And then we take an image one at a time and infer it. This is the full flow. So you can find lots of inference examples in the Openvino web page. Here I will try to run the full pipeline as described before. We call it tutorial 1. It's also available in the Openvino web. Okay, so we're running tutorial 1. You can see that video is being processed image after image. performance information per image has been displayed along with a summary at the end. So you can see the summary, and we can see that the pre and post stages, which also include the decode and encode, take very little time per frame. Like you see here, 8 millisecond and 1.7 millisecond. Most of the time is consumed on the inference itself. Here, the machine on the machine that I used, this SSD model is using 32 milliseconds for the inference. So let's try to remember this number. Okay, so I put it here, and now let's try. Now let's try to run the same code with the same model on a GPU. So this is one of the nicest thing about the Inference Engine. When we want to run the integrated GPU instead of CPU, it will just take a different plugin with optimized functions or kernels or layers coded in OpenCL, already optimized for the GPU. So no need to recode anything, just change the flag to -D GPU, as you can see here. And note that I'm using an FP16 weights, not FP32, which are more optimized for the GPU. So let's run it. And here are the inference results. So you can see that the inference time dropped from 32 milliseconds to 20 milliseconds. We moved from 30 frames per second to almost 50 frames per second, just by moving to the GPU. And by the way, many people don't even use this GPU or even aware of its full capabilities. So let's run another experiment. Let's run on the GPU, but now let's run with high batch. So I'll try batch 16, meaning I'm going to take 16 frames that are being packed into one blob and being inferred at once. Again, no coding required, just add -batch 16, and I'm running, and you can see that the inference now is dropped to 12 milliseconds. I think this is pretty cool. I mean, by moving to GPU and then moving to batch 16, we got like 2.6x improvement, and moved to 80 frames per second. And now I can easily try other batches or combination or FP32 or 16 to find the best performance for my system. Now let's try to run it on a Movidius stick. So this is totally different architecture, but still there's no need for recoding anything. The only thing that we need to do is to change the flag, the device. The Inference Engine is supporting multiple devices just with a flag. Here I just specify -D. My device is Myriad. That's all. And same goes to FPGA and other devices in the future. But what if I want to run portion of the network on one device and portion of on another device? So Inference Engine also has a hetero plugin. Here, for example, topology will run on GPU, but if a specific layer doesn't have an optimized kernel for the GPU, this layer will run on the CPU as a fallback. So this is a real heterogeneous option. Inference Engine also supports extensibility. In case you'd like to code your own custom layer, it is possible. You can code C++ for CPU custom layers. You can code OpenCL for GPU custom layers, etc. You can find examples on the Openvino web page, and we're done with inference. So we're happy. We got the performance we were looking for. How about the rest of the pipeline? For traditional computer vision, we recommend OpenCV. Again, many examples on our web page and all around. Tutorial 1, which we just ran, will show you exactly how to process a video, prepare it for inference, and do all the post-processing using OpenCV. OpenCL is our recommendation for building custom GPU functions. Lots of materials could be found on the web. You can program OpenCL for GPU and for FPGA and for more devices in the future. So maybe it's a good time to say a few words about our integrated graphic engine. This is Skylake, for example, Core 6 generation. You can see that the GPU at the bottom is taking a considerable amount of silicon. And Skylake have 3 flavors of integrated GPU. We call them GT2, 3, 4. The external names are HD graphics, Iris, and Iris Pro graphics. GT2 will have 24 execution units, basically mini cores that's doing the actual computation, but also contain other fixed functions for media acceleration. GT3 will have 48 execution units and 2 media acceleration, and so on. The execution units, which were originally built for rendering vertices for 3D graphics, can do today much more. For example, they can run inference, they can help with encoding, but on top of them there are other functions in the GPU. There are the VD box and the VE box. And these are pieces of hardware that can accelerate your decode, encode, and image processing. Even if your execution units are fully utilized, you still can use them to accelerate other tasks. In order to access and use this fixed function, you can use Intel Media SDK. Intel Media SDK works on Windows and Linux. It supports decode, encode of multiple formats, a lot of image processing functions like resize, scale, color conversion, denoising, many of the most used image processing functions you will need. Download it, look at the samples, and use it. If you have an Intel GPU in the systems, it basically means more resources for free, as the VDBox and VBox are probably sitting idle for you. Our tutorial 2 is using Media SDK for decode. Our tutorial 3 is using Media SDK for image processing. Our tutorial 5 is using Media SDK for everything, for encode, decode, image processing. Use it to learn how to do it. Use it as a reference. So after we implemented the full pipeline and utilized all the resources of our system, let's try to analyze the activity of the system to see if it's really fully utilized. As an example, I'd like to show you how the GPU hardware looks like using VTune, which is part of Intel System Studio. We will run tutorial 4, just like before. We will run it on GPU, but we'll only run 4 frames. You can see here flag-FR4. So what will happen is that we will load the model and then infer 4 frames, one after the other. I'm running an analysis called GPU Hotspot. At the bottom you can see the 4 cores activity. Only 1 core is active during the load of the model. You can see that. And 4 of them are used when processing the frames. At the top you can see the GPU activity. Again, no activity when we're loading the model. Let's try to zoom in. So you can see the GPU activity when loading the weights. and when running the 4 frames. You can see the four inferences happening. And let's zoom in further. And now we can actually see the execution queue of the GPU and the names of the layers being executed. I can see here convolution, pooling, etc. The annotation of the names is done by ITT. You can look it up the web, ITT code. It's pretty easy to implement and to label portion of the code, and it's very useful. So, putting and trying to analyze, I've demonstrated the use of Media SDK and Openvino and other tools to build a real heterogeneous workload for video analytics. We talked about running inference, computer vision, and media on various devices, and I hope you can just download these tools and start using them right away. My recommendation is to start by writing your code on CPU. Use OpenCV, meet the accuracy and functionality targets, and then go into iterative trial and error procedure to optimize it. What you usually need to do is to identify the critical path, where is the critical task, and then try to offload it to an accelerator, whether it's a GPU, FPGA, or video-based, and then measure the utilization performance. And then do it again and again until your system is balanced, fully utilized, and give you the performance that you need.
Okay, thanks, guys, for that introduction. Tabo, would you like to take the floor?
Yeah, thank you everybody for being through with us today. I hope that you really found the resources and the material interesting, and you would maybe be interested into building more solutions or even integrating artificial intelligence in your projects. We wish you well, and we actually going to be having a hands-on Intel DevCloud. So this is where it allows developers to actually test out or perform these heterogeneous executions, as our friend Andrew has said earlier. And now we have it on the cloud, which is totally low cost. A total of cost of ownership is literally close to zero, since it's open to developers. And today we will be having a DevCloud hands-on, and we will be having okay, thank you. So DevCloud for the Edge, it's actually where you have the Openvino orchestrated on the cloud. So all these kinds of workloads that Andrew has been talking about earlier, you also find this on the link. If you want to go to DevCloud, you can literally sign up now, and we will have hands-on until time. And you also have to gain valuable insights and how to use the cloud into it. So I'll quickly jump to.
Yeah, I think now is a good time for everybody to just sign up.
Yeah.
Before we start.
Before we start now.
Yeah.
Okay, so I think I will give everybody around 2 to 5 minutes, and then please just text down on the text box, and if you are ready, and then we can start. Okay, so here's the tutorial, guys. I will also send you a link to this tutorial after you've signed up. Then you can straight go to the tutorial. Okay, guys, I will also take you through the process of signing up. I hope you've actually went through to this link down on the chat. And so when you sign up, you get into this page that you can see on your screen right now. And then you go up here. It will show you a sign-in page. And then you just sign up and then sign in. And immediately when you're done from there, you can go further and then come to learn. There are certain tutorials that we will be having today. Today we're having an object detection tutorial. So I'll just quickly scroll through the one we will be having today. Yeah, object detection. There's one here. But for me, I've already loaded it here, so I don't have to really load it again. So I will just pause it here and then just give you 2 minutes. When you guys are ready, I will just jump in the tutorial. Thank you, guys.
Excellent, guys. I hope everybody is ready now. If there's any problems, you can just raise up your hand now, or turn your mic on. Okay, cool. Then we'll assume that everybody's ready. So DevCloud is a developer cloud offered by Intel, mainly to help developers to test out their machine learning workloads using different Intel processors, such as Intel CPUs, Intel VPUs, Intel FPGAs, which are field programmable gateway arrays, and also vision processing units, such as MOVIDIS. And so it helps developers to choose and decide on which hardware they would like to use for their project without actually having to buy the hardware first. And it's very good for testing out high throughput models and also very data intensive models. So today we'll go through the object detection tutorial, which uses the MobileNet SSD model. As you can see right here, this is the model that is used. We did not train the model from scratch. We're just going to reuse the model that was already trained by Google and the likes. Okay, and then we've got the labels, some of the labels that we will use for the different classes. And we've got an image that we're going to use for testing, for faces, and then we've also got an image of a car that we're also going to use for text. So this is some of the prerequisites for this sample to run. So if you would like to perhaps maybe download this notebook and run it on your local machine, then you would need to also download these folders as well. Okay. So a brief introduction about Openvino was done by Andrew. I think it was very in-depth. Does anybody have any question at the moment about Intel Openvino Toolkit? Did everybody understand how the different pipelines operate, such as the decoding up until the end of the encoding? Excellent. So I think that's the main point of using the Intel DevCloud for the Edge. It is to use the Intel Openvino Toolkit, which helps you to perform inference on any hardware that Intel produces, and even many other more, such as ARM and such as NVIDIA GPUs can also use the Intel distribution of Openvino Toolkit. But so if you want to make your models run a little bit faster after you've trained it, then this is the tool that I would use for that kind of workload. Okay, and it's got a lot of pre-trained models that are hosted on GitHub. I think over 100 pre-trained models for different use cases, such as person detection and things such as like collision detection, activity recognition, and also medical image processing applications such as pneumonia classification applications as well. Today, in the afternoon session, we're actually also going to be doing a live demonstration of the robotic segmentation sample demo application, which is very good for healthcare scenarios where you would like to develop robotic surgery robots. So we will go further on to just start off with the simple one where we detect aeroplanes, bicycles, birds, boats, and buses. So modes of transportation will be the different classes that we will be working with today. So we're going to basically take an image and then we will make inference on whether there is an aeroplane, a bike, and a bird, boat, bus, and such and such. Okay. So what are the key concepts that we're going to learn? The key concepts would be how to actually implement all of the stuff that Andrew was talking about, how to download a pre-trained model, and then also convert it into an XML and a bin file, which we call the intermediate representation format, and then execute inference on a processor, such as CPU, VPU, and so on. Okay, so For this tutorial, the model was trained using CafeNet. So Cafe is a framework from UC Bartley that helps developers to create machine learning models, particularly for computer vision workloads. So what we're going to do here is that we're going to use this model that was trained using CafeNet, and then we're going to run the model through the model optimizer, which is one of the key components of the Intel Openvino toolkit, the model optimizer, to produce an optimized intermediate representation format. So in this format, there's only two files that exist. There is an XML file and there is a bin file. So these are the intermediate representation files that you will get after you've run the model optimizer. Then we will use the model optimizer IR files and load them inside our application. So this is a user application depending on the use case. And our use case is to detect modes of transport such as aeroplanes, bicycles, and buses. Okay? So just three basic steps that we perform. Quite easy, right? So it's the first part is the green part, and the middle part is the Openvino one where we run the model optimizer and load it inside the Inference Engine. And then from there, it goes to the other green part, which is the user application. Okay. So the Inference Engine uses an integration flow for its API for you to communicate with the APIs. So the first one is that you will load the plugin that reads the model IRs. So this plugin will take it as an input, the XML and the bin files. Then load the model into the plugin, prepare the input, and then run inference on it. And by inference, we mean now utilize or operationalize the model. And then process the output. So then maybe output a video or maybe output an image with bounding boxes and also the accuracy of the detection model for that object. Okay, so for input processing, Intel Openvino toolkit uses OpenCV. So OpenCV is an open computer vision library. In this case, we will use it to perform some resizing on the input data. So if the input data is an image, then we will resize the image into the correct input format that we would like it. So say perhaps you want it to be 180 by 180 or 224 by 224, then you will resize the input such that it is acceptable by the model. So the model has its own input size, which you would now need to pre-process this image before you feed it into the model. So OpenCV is very good at that. It's basically just one line of code to do all of this. You can do a resize. You can also do a frame transpose and also a frame reshape in the same line. Not very difficult. Okay. So the sample application imports a few other libraries besides OpenCV. We've got also a time tracking module. This time tracking module is also used. We also use the Openvino Inference Engine library. And then we also use matplotlib, which is used to plot and display the output images. Okay, let's go ahead and run that cell so that we input the libraries. Is everybody following? Does everybody also have? Okay, I think there's somebody who wants to join. Okay, excellent. All right, guys. So I hope that you also have run the import all those libraries. Okay. So now we're going to download the model using the model downloader. So remember in the beginning, Andrew mentioned the model downloader can be used to download pre-trained models. Over 100 pre-trained models that are hosted on the Intel Open Model Zoo. Let me just show you it on GitHub. So this is the Open Model Zoo, which has all the models that you may need. You know, instead of you training your own model, you could just basically use these ones if they fit your use case. Okay, so we're going to use a model from there, and this is how to use the model downloader. You would have to give it the name of the model that you want to download, and also the output that you would like it to be, and the output directory for it. So we're going to say, okay, give us model MobileNet SSD. SSD stands for single shot detector. So this MobileNet model is a single shot detector. Okay. So then we're going to use converter.py with a Python script to convert the model that are not in the Inference Engine IR format into a format using Model Optimizer. Okay. So let's run both of these ones. So this is to obtain the model. You could do this on your local machine as well. Okay, so you could run this command on your local machine as well. Okay, so let's convert the model into an IR format. Excellent. So you can see that the model that was downloaded, the raw model that was downloaded is this one. And you can see the format that it was in a cafe model right here. Okay, so we've now optimized this model into an intermediate representation format through just one line of code. Just by executing the convert.py, and you give it the name of it and the directory where it is in, and then the output. So the model optimizer then converts it into an intermediate representation format here. As you can see down here, MobileNet SSD.bin, and the other one up here, MobileNet SSD.xml. So now that we have converted the model into an intermediate representation format, we need to now configure our application so that we can use it. We can use or operationalize these models. Okay, so to operationalize it, it's going to be a simple, we're going to write a simple script that will take as an input the model XML path, the model bin path, and also the input path of the image. And this could be maybe a video, or also it could be a live video using your camera on your laptop or whichever camera you have. And then we're also going to take another input of a device. So the device could be on a CPU or on a GPU or on a FPGA. So depending on the device, that will give that as the input. So you can change this, and you're going to see as we go down in the tutorials that we can run all of these workloads on a CPU, GPU, FPGA, and on a myriad in parallel on the DevCloud. And then at the end, what we can do is that we can then compare the performances of all of these devices, and then select which device works well with our model. Okay, cool. So let's go ahead and set that. As you can see, this is just basically setting the directory of the model. And if this was on your local machine, then this directory would need to change. Okay, and then our OS path library that we imported has now come in handy here, which then finds the corresponding .bin file. Okay, and then the input image, our input image would be the car.bmp, and then the CPU extension, and then we set our device to CPU for now. Okay, we could change this to GPU, we could change it to VPU as well, or FPGA. And then the labels.txt, these are just the labels such as aeroplane, bicycle, and also some other modes of transport as well, okay? Okay, the probability threshold, which is the minimum probability to detect an object, we'll set it at 0.5. If maybe your project requires a high level of accuracy, you could set it to 90%, depending on your use case. But you know that theoretically, it is not possible to get a probability threshold of 100%. It doesn't make sense, okay? So just set it to something that theoretically makes sense. Okay, cool. So let's go ahead and run the model the application configuration. Excellent. And then we're going to create an Inference Engine instance using the IE core function. Okay, cool. We've created an Inference Engine object. Let's go. So now we're going to load the network from the IR files. So from the IR files, we mean the XML and the bin file, okay? This is how you simply load them, using the IE, which is the object that we've just created, okay? Cool. And then we also check to make sure that the plugin has support for all layers in the loaded model, okay? So then to do that, we use the object that we just created, and then we query the network, and then we query the network with the device, okay? Perfect. Let's go ahead and run that to check and make sure that the model's input and output are what is expected. Okay, the model files have been loaded and verified. So you could do this as well to verify your models and its different topologies, whether they are supported by the Inference Engine. If it's not supported, I think just reaching out to some of us in the community and also in the forums would be a good shot, because some of the models and topologies that are not supported, we've got tutorials on how to make that supported as well, by writing your own custom model topologies. Okay, so just reach out online, and I'm sure somebody can help you build your own custom model and add your own topologies to it. But for pre-trained models, it's also good to always check whether the model topologies are supported. Okay, cool. So let's run the let's now execute the Inference Engine, you know, and then so that we can start performing some outputs on it and performing some inference. Okay. Is everybody following, or are there any questions at the moment? Okay, cool. We shall move on. So now we load the labels, but remember we said the labels are for cars and persons and such. So let's load that as well. And then remember the OpenCV library that is used for resizing and denoising the picture. This is the part where we can now execute that with a simple line down here. So defining the function for resizing. Basically, this happens, you take the input of an image and then give it the width and the height. Simple as that. The same for transpose and also for reshape. And then it returns you the in-frame for that. And then we can use this as the input because we know that it has the correct input size for the model. Exactly. Because if it doesn't have the same input size for the model, let's say, for instance, the model is 224, and you give it an input size of 180, then the model will run, but you know it might give you misleading results. So just to do the image resizing is very good to make sure that the results that you get are true. Okay, so let's go ahead and run that. Excellent. So this is the picture that has been resized. So the picture has been resized from 637 by 749 to 300 by 300, which is the input of the model. Do you see why that is important, fellas? Okay. Cool. So now we're going to run some inference on it. Okay. And to run inference, we're going to take the input blob, which would be the model, or the IR files, which is the XML and the bin, and then the in file, which would be the resized image. Okay, and then calculate the time from start to end while we do it using the time library that we imported. Okay, inference complete, and it took 38.68 milliseconds. Okay, so let's process the results. Okay, and then let's display them. So the processing of the results is just some simple changing of the picture. So drawing the rectangles that are needed on the picture after we've detected the label, and also putting some text of the different label and also the probability of it. Okay, so this is just for the drawing of the box and the labels. And then after we're doing that, we want to now display that result. It took about 38.86 milliseconds to perform the inference on it. And this with 100%, this is a car. Excellent. Any questions at the moment? Is everything clear?
Okay, guys. I think there's no questions yet, but we'll continue. Feel free to stop us, ask us along the way. We'll just answer your questions on the chat, or you can just raise up your hand, and yeah, we'll attend to the question. So as previously Mulodi has been saying about the inference engine, is that you can run multiple inferences on different hardwares, and as well also prepare the images that are actually fed into the model. So these operations that you can do to actually optimize your model and make sure that your model does have a high accuracy, and it's also optimized on Intel architecture. This can go to your CPUs, your GPUs, your FPGAs, and so forth. So we'll do this exercise one here. So we run on a different image. As we saw earlier, there was 2 cars, and we're able to detect that this is a car with 100% accuracy. But as we say that it's close to 1 or it's 0.99%.
Yeah.
This is just inference.
Yeah, so we rounded it off.
Yeah, we rounded it off. So now we'll quickly run on another image where we'll define an inter image and then input the process image, and then the results will be processed, and then they can be used again on the tutorial again. So this gives you, when you're running over images and videos, and you can think about videos, it's actually multiple images inside a video. So it's very important to, your model to read all kinds of images. So now we do have this one. It's actually converted from 787 to 1180 from 300. So from both 787 1180 to 300 by 300, which is your height and your width. And then there we have the detection. We see it can carefully detect the person with a 84.6% accuracy. That's pretty good. And so this is the mobile net popular network that is out there, and it's publicly available. So Openvino really helps you to take these kind of models and use it within your applications or pipelines, whichever may be your scenario. So now we can run on optional image. So running on your own image, it means that you now have the new data you're trying to feed into your model or the application. So for instance, let's say you are running a security premises and you want to find out the activity, what are people doing in a certain scenario, if that maybe actually might spark some insights to your business scenario, then you can use your own data set or videos just to infer and then find out, in real time, what might be happening, what are the alerts, and then you can, have actionable data, and then you can do something about it, So now we'll just run here, and then on the script, I'll just quickly go through it by line. So you just input a local file. Now we get the local file from online, which you can see is hosted on github.com. And as well, okay, let me check. I think there's a question or someone is joining. Or raise the hand. Okay. Hey, definitely. Yes. Do you want to ask a question?
Yeah, totally. The name is Delphine. Okay.
Oh, Delphine. Hey, sorry about that. Okay.
Okay. I'm good. So I'm sorry, I just pumped in like some
No worries.
minutes ago.
Yes.
About creating your own data set. For
Okay.
instance, if you have like 100 images, will this the code you're providing, that like the input path, will you have to do this for 100 images, or is there a way of just putting it in a single folder, then referencing that when you're creating your own data set?
Yes, you can actually do that. Here we just making an example, because this is just a standard getting started tutorial, and so it's actually showing on single pictures. But yes, you can actually do it with folders, and literally just go to the folder and then index those images.
Yeah.
From the folder.
Yeah, I think you could do that with the for loop.
Yeah.
Yeah, and then you just loop these functions inside that for loop, and then you could run it through different images. So if you've got 1 million images, you could just run all of those images inside a for loop using the Inference Engine. It's very, 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 very good. I think also the next one on running a video.
Yes.
Would be more suitable for you, because I mean a video is basically a lot of images in one. But to answer your question, definitely. Yeah. But also, Delphine, do you want to train a machine learning model, or do you want to run inference?
Yeah, I have been stuck this for like 3 months, and I was like, thank God you guys are tackling it. So I wanted to learn a model where it just looks at an image and says, this is a deprived image, and this is not deprived. They're just fancy words. Like, this is an image from a poor neighborhood, and this is an image from a well-to-do neighborhood. But I've been running in circles with this. So when Roti was presenting, I was like, yeah, if this can be done, like even in like 10 images, then someone can just duplicate that into 50
Yes.
images. But if there's a material or something, that would really, really help.
Yeah, this material, there's a script that we have. Let me show you. I think it's called Openvino notebooks. Yeah, let me just, yeah. So it's got a collection of notebooks that you could use to even train a machine learning model. And then once you've trained the model, to deploy it. Let me just share this in the tab. Perhaps maybe
Let's
other people also would like to see it. So this is what we call the Openvino notebooks. And part of the notebooks is that it is a collection of ready-to-run Jupyter notebooks for learning and experimenting with Openvino Toolkit. The notebooks provide an introduction to Openvino basics and also teach developers how to leverage our API for optimized inference. Okay, so there's a lot of examples that you could run in here. There's one particular one that I found interesting recently. Oh, I think it's this one that you're looking for. You're looking to train a model, and then after that, you also want to convert it into an Openvino IR and run inference on it. So you could use this one, and it's got everything that you will need for
inference.
From training, how a picture comes from your village or from township to how a picture looks like from South African township or South African village, you know. So if that's what you want to do, this is a perfect example on how to use TensorFlow and Openvino together. You can just go inside one of it, you'll see and it's got some very, very informative information. Yeah, let me just share this in the chat. But yeah, as you can see, you're going to train the model. And then after you've trained the model, you're going to convert it into an Openvino format, and you are good to go.
Oh, yeah, this sounds amazing. And also, would you please share your slides after the presentation? Would you like to follow along?
Today we don't have any slides. We haven't used any slides. Andrew used slides, but those ones are proprietary, and so
I'll share the video.
We'll share the video with you. Yeah, is that okay?
That's okay, thanks.
Yeah, we'll share the video. Okay, let me share this in the chat for you so that you can go through the notebooks.
That's a really interesting project you're on, Delphine.
Yeah, it's what is it? This volunteering type of open source map thingy that I'm doing. So we are trying to just be able to cluster images from different parts of Africa.
Yeah.
In order to maybe like advise, is it these policymakers to not marginalize certain places because this is what they are, and yeah,
No,
just
that's
doing that.
wonderful.
Yeah.
That's wonderful, Delphina. Okay, so this will definitely help you. The part that you should watch out on is actually just the simple one, where your data set is. So a link to where your data set would come from. And then you change the name to the folder that is of that zip file, and you should be good to go. Okay, I think, Tabu, we can go back to the tutorial.
Yeah. I hope we answered your question, Delphine. Thank you, Delphine.
You have. Thank you.
Okay, great one. So as we'll take a note on that. Yes, you can run on multiple images, and as we saw from the previous notebook, you can explore the data set as much as data you can have. Openvino will be able to help you inference, those multiple detections at the edge, right? So we'll just go line by line here. We just input an image, standard inputting image command, and then we plot the axis, and then from there we show the image converted from BGR to RGB, the color conversion. This is actually based on your input of your model. And then we infer the image. It's an infer image function. And then from there we display from BGR to RGB conversion. So these are the inference results. And then from there we create the figure of this. Will be able to display or plot the actual detected image. So quickly run this. So guys, with notebooks, things are easy. You just go through these commands and run them with these snippets of codes. You can see we are actually on snippet 15, and it will automatically do all these functions at the same time. And then here's our model. There's a pre-processed image to 300 to 300, and then these are the inference results. You can see there's a car, dog there, horse, and a human being there, which is a person. So the mobile net has detected 5 classes in this image, as you can see, from horse to human being. So now we will actually now do a more video-based inference. And as we said that, pictures are just frames inside a whole total video. So now we're actually having an inference on these frames. So now we'll actually use cap.isOpen. This is a function that opens your camera. It can be a USB camera, it can be an internal camera of your PC, or any camera that is connected to the network. And then from there, we start reading the frames, which are those small pictures inside the video frame. And then from there, we start running our detection each and every second. So our speed of the model will be actually measured using frames per second. So how many frames are read each and every second within the video. Then now we'll do a matplot notebook. We import matplot to plot the image, the video, sorry. And then from there we input the path of the video. And as well, you can inference on multiple videos as well here. As much data you have, you can actually run heterogeneous execution. So what's really nice about Openvino is that you can run on multiple devices, and you can see the performance of your model on how well it runs on CPU, your GPU, and other dedicated processors. So now you load your video, and then you will capture your using the video vision library CV2, and then you capture that the video input path. It goes straight to the input path, collects the video here. It can be large folders, and then also now you will have that while loop. That snippet was here earlier. So while loop is just going through the frames of the open camera. This can be a video, this can be a real-time camera from your cell phone, whichever camera that is actually available or actually using in your solution. And then from there, we go through a while loop. Each and every frame, we do additional frames, and then if statements for us to actually skip number of frames, then infer max frames from there. So maximum number of frames that can be actually be read through the algorithm. And then from there, we display, right? So I'm quickly going to just run on this video here. It's hosted by GitHub. Oh, sorry, no, we have a data here. So it's a folder within this notebook here. So will be running from this folder. I'll just quickly run it and also wait for it. Okay. So there we go. It's a bit slow. Oh, it's still loading the video. Let's wait for it. So these are detections that it can actually detect. It's a bit slow, so I bet here we're using the CPU, and that's what I've actually pointed out, and Lodi as well said about it earlier, is that you have to find out which kind of processor does work best for your project, and for this one, we're having possibly a CPU.
Yeah.
Yeah. So for a CPU, that's how it runs. But also for cloud, you can use your Xeons and but it's actually today out of the scope of running through different accelerators.
Yeah.
But this is how it
So, Moloti, hi.
Yes.
We are running it on CPU, right? That is what you said. What if we
Yes.
want to run on GPU? Is there any other option, maybe
Yes.
some other option to actually run it to make it faster?
Yes. Definitely.
Indeed. Yeah.
So yeah, for this.
Where are the options where we can explore that?
Yes. So you can just come here to learn, but then there's more advanced samples. You can come here to.
No. I want to run the same sample what you are showing right now.
Okay.
Oh, in the same script. Okay.
Yeah.
So you can just go.
How
up.
do you know that this is CPU? How do you know that this is CPU, not GPU?
Oh,
Reset it.
Wait.
Wait, right here. So you can change this, and then you say no GPU.
Oh, okay.
And then you see,
And then it will work.
and then you run it on GPU.
Okay.
You see now.
So every time we'll have to set this to CPU, GPU, or VPU, or anything, whatever you want.
Yes. Correct.
Got
So
it. Perfect.
there's in the afternoon session, we're gonna do a more in-depth demonstration where we're going to run the workloads in parallel. So we're gonna run the same model on different hardware accelerators at the same time, and we see which one finishes.
Okay.
First. Yeah.
Okay. Sounds good. Yeah. Thanks, man.
My pleasure. Okay, Tabu, sorry.
Yeah. So so that's why we said the latency here is a bit slow. So the CPU, and also on the later tutorial, they will be more focused on accelerators. So here we're more focused on Openvino, getting a pre-trained model. I think our key takeaways here will be in a publicly open model from a different framework, and then we optimize the model to be Openvino compatible, which is your .xml and bin file, as Melody illustrated earlier. And then from there, you do have your Inference Engine, which is part of the Openvino toolkit, which will be connected to your application logic. And from there, you are ready to start inferencing using your Python application or whichever may be C++. It's just totally up to you which language you use. But here we're just showing, the method of inference and how to quickly time to market your solution, especially when it comes to inference at the edge. And this helps developers to go through the process.
Yeah.
And when you do have the application, running locally or on a server cloud, you'll be ready to just execute these models, and then finding out if your model is fine-tuned, optimized on Intel architecture, and then I believe that you're good to go.
Yeah, and I think I like the way that the model isn't working properly on CPU. if somebody had bought a CPU and thought that that CPU would be good for the machine learning workloads, you can see that that can be very dangerous for projects. You know, if you buy a machine that doesn't necessarily perform optimal. So Intel DevCloud helps you to decide which device works properly, such as CPU or GPU or whichever one. You know, so I think it's very good. For now, we will leave it here. I think, is there anybody that forgot maybe to sign up for DevCloud? If somebody forgot to sign up, I think it's a good time to just sign up and then maybe go through this tutorial and check out the other tutorials. Yeah.
Thank you. I think we'll open the floor for questions, and we'll just give it around 5-10 minutes. There's a chat open. Raise your hand. Open a mic. We are ready to attend to your question.
Yeah.
And so to wrap it up, I think we had our key takeaways where we can run the images, videos, because since we are in computer vision, and optimize these algorithms from TensorFlow, Caffe, all these popular frameworks that are out there, and then optimizes on an Intel architecture. And then from there, you can run inference on edge devices. So this will be a matter of your choice, which devices you are going for. This is actually in the space of IoT and AI systems. So this will actually give you a starter breakthrough. We don't know, but if you are ready to go through here, signing up is really easy. It's just a matter of few clicks, and then you're ready to evaluate your model, and also sample notebooks. If you want snippets of code that you might want to use in your application, feel free. It's totally open. It's open source. Yeah. So for this one, we will just clean up the data that we just downloaded, and then just leave our virtual machine clean, and we'll be ready to start again. So it's actually just for good practices. For data projects.
Wonderful, guys. No, thank you so much. Thank you, Mohammed. Thank you to everybody else who attended. It was lovely to have you guys there. We hope that you guys have learned something, and we are available on LinkedIn if you need us. We have a question. Okay.
Hi, my name is Avuzwa.
Welcome, Avuzwa.
I'm not sure if it's relatable to what we were learning here, but I wanted to ask, I'm diving into game development, and I saw on some of the tools on Dev Intel that there's gaming in there, and I'm not sure of the type of machine that I should be using, because with me, I've been so stressed out. I only have just a laptop, which is a Lenovo E540. And I think the core is i5. It's Intel i5.
Yeah.
So I don't know how big, or is it strong enough for me to dive into game development, or I would need to, dive into cloud, have a virtual machine, or can I still push myself?
Oh, excellent question, Awuzwa. I think it's i5. It works well. i5 is perfect. The machine that we're using right now is actually i5. We've built a couple of games using i5. I think the framework that you should use or the game engine needs to be Unity.
Okay.
Are you familiar with Unity game engine?
I'm familiar with Unity, but I had picked Unreal because I think that's what we're going to be using as a team. And then a lot of people are just complaining as to Unreal is too, it's kind of like Android Studio. It just kind of heats up your laptop.
Yeah, Unreal is not optimized for Intel architectures. In my experience, Unity works perfect.
Is it?
Yeah, and you know, for also distributing your applications, it's so much better than
Unreal.
yeah. And also, I don't know about the language. If Unreal is mostly C++, if I'm not mistaken.
Yeah, that's correct.
And Unity is C#,
Yes, that's correct.
which makes life a little bit easier when you're in C#. C++ just adds a few more weeks to your work.
Okay, not a problem. Thank you so much.
My pleasure, my pleasure. Okay, I think maybe there's a tab called gameplay.intel. Have you seen it before?
Is that question for me?
Yes.
Oh, yes. I was browsing through it as you were talking.
Okay.
Right now on the development, and I signed in and I saw something with game, but I can't go back now. Visual computing graphics, I don't know, I'm not sure, but no, I saw it somewhere.
Yeah, so this is gameplay.intel.com, and if your game works well, we can help you distribute it through here. Most popular games are distributed here.
Oh, okay, beautiful. Okay, I didn't see that.
So all of these games are Intel certified and Intel optimized games.
Oh, okay.
Yeah, so this is an excellent program for you to get involved. And we can introduce you to a guy called, he's our chief nerd. He calls himself Nerd Herder.
Okay.
He's the boss of the, what's that? Nerdzilla. That's what they call. So his name, what's his name again? Eric Martian. Eric Martian is the nerd herder for all games on Intel. So we can introduce you to her. Are you on LinkedIn?
Yes, I am. I'd love to meet her.
Okay. We'll connect you with her during the course of the week.
Okay, thank you so much.
Welcome. Okay. A very interesting question about games. Hey, Charles, yes, you may go forward. Charles? Is he gone?
Hey.
Oh, sorry.
Can you connect?
I was on mute.
Okay.
Okay.
Yeah. So I'm not too sure if this question is related to what you are going through, but I want to know how far behind is SA with AI and how many years will it take us to catch up?
Sorry?
How far behind is SA, South Africa, with AI, and how many years will it take us to catch up?
Very interesting question. I think I'll leave it to Tabo.
Okay. Yeah, to be honest, my friend, AI it's fairly new, and it's actually being deployed here and there. So I think there's an open room for the whole world to catch up, because